All right, the next formula I'm going to show you is a way to take a group and partition of, suppose I have n objects in the group, and I want to partition that group into k distinct groups with sizes n1, so the groups themselves don't have to have equal sizes. And it's best understood with an example. The formula of the number of ways I can do this is n factorial divided by n1 factorial, n2 factorial, dot, dot, dot. By the way, all of these formulas are really just the multiplication rule. And unfortunately, one of the worst things about being a mathematician is you feel that you're entitled not to memorize formulas. So we never finish standardized tests because we sit there and try to derive everything. Which you can derive it through the multiplication rule, which is cool, but don't do it on a standardized test. So I recommend that you read through example 2.10, which is really good from the book. I'm going to just go through this quickly to illustrate how to do it, but this is straight from example 2.10. If I have 20 laborers and I have 4 jobs and I have to assign them to these 4 jobs, but the first job needs 6 people at them, that's my N1. My second job needs 4 people. My third job needs 5, and the fourth job needs 5. So you see how I've labeled them N1, N2, N3, and N4. That was not in the example. This is me figuring that, I guess the hard part of this is I know I need to use this formula. How do I know that? Well, I know that because I have 20 people, and I'm breaking them up into a group of 4 jobs, and the 4 jobs have those 20 people scattered around in them. The problem does more. It actually looks at some probabilities. So I'm encouraging you to please read this problem carefully through. Just to let you know, the size of the entire sample space would be the total possibilities of ways I could arrange these people so that 6 people ended up for job 1 and 4 people ended up for job 2 and so forth will be given by just plugging into this formula. All right, the next formula is how to count the number of ways to choose a k element subsets from n element sets. When in a combinatorics class, you always get this from how to select your basketball teams. But you have seen this before in 206. You saw it with Colonel Watts. This is the binomial coefficients, or the coefficients in Pascal's triangle, which I absolutely love and adore, but I'm not going to show you. I'm just going to give you the raw formula. It's n factorial divided by r factorial, which was the permutation formula, divided by a little bit more. And in this case, order doesn't matter. So I just want to show you something because it's really neat to understand this, because I think of this as modding. So if I have the permutation formula, which is n factorial divided by r factorial, I am dividing by more. So I'm actually getting less. This number is going to be less than what's given to you by the permutation formula. So what is that? So if I have 3 things and I want to look at the number of rearrangements, the permutation, number of permutations, when order matters. When order matters, ABC is something different than ACB. Well, the total I'm going to get is 3 factorial because it's 3 times 2 times 1, but I can list them all out and see that it's actually 3 times 2 times 1. There's 6 different rearrangements of the triple ABC. Now, if order doesn't matter, what happens is all of these guys turn out to be the same thing as the first one. So order doesn't matter, and I get something less. In fact, I get only 1 left, which turns out to be 3 factorial divided by 3 factorial, which is 1. This was what we call a toy example, but it was an example just to show you what these formulas really are. And if I had you in a combinatorics class, I would actually have you discover these on your own. And if you like this stuff, there's a great book I can recommend that's free online. And in the few days that you have off somewhere, you can sit around and work these nice examples. Beautiful stuff. Okay, I refer you to examples 212 and 213 in the book. I'm going to go through 212 carefully so that you can see what it's about. Suppose I have the event that's a subset of the sample space, that exactly one of the 2 best applicants, so I have 5 applicants for a job, and I grab 2 out of these 5, and I want exactly one of the 2 best. So I arrange the 5, there's 2 of them that are best, and I want to have exactly one of the 2 best applicants appear in my selection of 5. Well, when I write this, I mean cardinality, number of elements in the set. That's when I put these absolute value symbols of A. So they want to know the sample size. They want to know the how much is in that event, the size of that event, and they want to know the probability of A. So in this case, how do I know how many things are in A? Well, there's 2 guys I could get in there, right? I have to count the number of ways of selecting one of the 2 best. And I also, that means that the other guy in the 2 best has going to end up in the pile of the 3 worst, right? No, I said that wrong. So the number of ways, I'm going to pick 2, and I've got to get one of the 2 best in that 2, but the remaining one is going to be with the 2 worst. So the size of A is going to be, this 1 here stands for there's 2 good guys, and one of the good guys is going to be, there's 2 good guys total. One of these good guys is going to be selected in groups of 2. One of the good guys would be in the remaining group of 3. So there I said it better than I had in the past. It's a weird problem. So the first, it's multiplication rule with chunks. So the first chunk is that I have to look at the number of ways that I can take this 2 guys. I'm going to take a group of 2, pick 2 out of the bag, and one of them has to be in that group of 2. Then, in the remaining 3, one of the other best ones has to be selected in that remaining 3. So I do this multiplication rule, and it turns out that I get something easy, which is 6. To get the probability of selecting the group of 2, with 1 being, well, I have to have the size of A divided by the whole sample size. The whole sample size, I'm selecting only, I don't care whether I have 5 people total, and I'm making groups of 2. These are, the top is the group, in the top what I have is the number of ways that I could select in that 2 and get one of the best. That's going to be a subset of the total sample space, which is just pulling a group of 2, pulling a group of 2. So these guys are just where I happen to have one of the best applicants in the group of 2, and this is all groups of 2. And so when I look at that, just so I wrote it down, all ways to form a group of 2 from all the applicants, and I get 6 over 10, which is 0.6. All right, I'm going to stop here, and then I'm going to go to some more definitions. Hopefully this was clear. I know I explained that a little bit messy, but hopefully it was clear what I was doing, and you could maybe see where those pieces of formula picked out.